Cosmology is a study of the structure and evolution of the universe. There are fascinating topics in cosmology, and you're advised to read about them in Chapter 18 of our text. This chapter includes a broader discussion about stars and our sun, but in our class we'll focus on topics brought up in sections 5 through 7 of that chapter. That is pages 520 to 537. Here we'll look briefly at two very exotic topics. That is black holes and the idea of the Big Bang. Did you know that Albert Einstein actually had two theories of relativity? The first was 1905, which was called the special theory of relativity, and it deals with relative motion between objects. The second was 1916, called the general theory of relativity, and it describes gravitational effects on space and time. In his general theory, Einstein suggests that massive bodies actually distort or bend empty space. And on this slide I mentioned the sun, but Einstein's general theory says any object with mass bends space. It's just the effects are more noticeable with large masses like our sun. This is really a remarkable concept. Black holes, then, are extremely massive bodies that bend space so severely that in a sense we say the space bends back onto itself. And nothing, not even a beam of light, can escape from the gravitational field of a black hole, which is why we call it a black hole. Again, truly amazing. Objects with mass at least 8 times that of our sun could in principle form black holes. Now let's use beams of light that travel through empty space to help us visualize how empty space can be warped or bent. At the right, we represent someone on Earth viewing the separation of the two distant stars. The long lines show the path that light takes to get from the stars to the observer. There's nothing unusual here yet. Now, let's view those two stars when light coming from them must pass by a large massive object, such as our sun, in order to reach the Earth observer. The light that reaches the Earth actually takes a bent path as it passes by the sun. And the question would be, how do we actually know that? Well, the Earth observer sees the stars as if they come from the end of the dashed lines. It appears the stars are further apart when light coming from them must pass by the sun compared to when it does not. So massive objects really do actually bend empty space. Wow. And this diagram shows an actual experiment, or illustrates an experiment done in 1919 by Arthur Eddington. There's some controversy on whether his measurements were precise enough to show the effect, but it's been repeated since then several times, and most agree that the bending of space effects as illustrated here are actually confirmed. Now, as we said, any object with mass has gravitational effects, and then gravity actually bends space. So now a black hole occurs when the mass is so great that the space is bent so that nothing, again, not even light, can leave the area. Now the center of the black hole is called a singularity. And it's illustrated there and marked in the bottom left diagram. At the singularity, the curvature of space and the density of the material are infinite. Of course, this defies human intuition. Then there's a sphere some radial distance from the center, i.e. from that singularity, which is called the event horizon, and that's also marked on that diagram. Once inside the event horizon, no further communication with the rest of the universe is possible. And the diagram shows that there's strong curvature of light rays that are passing by the black hole, which is due to the space itself being so bent in that area. But since the light rays are still outside the event horizon, they keep going. If they were to try to pass through the event horizon, they would disappear altogether. Amazingly, time itself is affected by gravity. Really? Yes, really. The time actually slows down in the presence of gravity. You've never noticed it personally because the difference in gravity that you've experienced is not enough to notice the difference in time. But this is a real effect. For example, GPS satellites high above the Earth, they feel a little less gravity than at Earth's surface, so their clocks actually run a little faster up there than they do here on Earth. This really happens, and to ensure precision, GPS satellites have corrections for gravity factored into their clock system. Now, Once the event horizon of a black hole is breached, time not only slows down, but it actually stops. How is this possible? I don't know, but I am challenged by advice given to Job in the Bible. In Job 37 we read, "Listen to this, O Job, stand still and consider the wondrous works of God." Well, I hope you found these ideas interesting and stimulating, and I encourage you to follow up by reading about them in your text. Thanks so much for joining me.